Accurizing is the process of improving the accuracy and precision of a gun, firearm or airgun. For firearms, accuracy is the ability to hit exactly what one is aiming at, and precision is the ability to hit the same place over and over again in a repeatable fashion. Both are the goals of accurizing, which generally concentrates on 4 different areas. Usability, enhancements that give the shooter a firmer and more consistent hold on the firearm, as well as a more consistent trigger pull. Better design ergonomics is often employed, such as adjustable buttstocks and grips with more vertical angles that are natural to the human hand and wrist, e.g. pistol grip. Spirit levels are often mounted to minimize contacting, which can vary the points of impact. Weapon mounts such as bipod, monopod, bench rest, shooting sticks or simply sandbags can provide a more stable and relaxed platform for the shooter, and devices such as muzzle brake or compensator can also be used to help counter the muzzle rise from recoils. The use of suitable slings can also help shooters to stabilize the aim when shooting offhand while standing or squatting. Tolerances, parts that better fit together will shift less, or shift more consistently, under recoil. Rifle bedding is one of the most common practices of such accurizing procedure. Adequate screw torque setting between the action and the stock is also important for the overall rigidity of the system. Some companies, such as Savage Arms, have even introduced features like floating bolt head to provide better bolt breech engagement and sealing of the barrel breech. Harmonics, the act of firing a gun generates a rapid pressure increase within the barrel bore, causing the barrel to resonate and vibrate in a whip-like fashion. The resultant harmonic oscillations of the barrel affect the terminal phase of the projectile's internal ballistics and in turn the initial status of its external ballistics, and therefore need to be minimized or tuned to limit their effects on accuracy. Generally, the harmonic effects are proportional to the square of the barrel length, and so are generally only of concern in long guns such as rifles but not handguns. Some external accessories, called tuners or deresonators, can also be mounted onto the barrel to modify the harmonic wave pattern so that the note is shifted as near to the muzzle as possible. Air guns have significantly lower barrel pressure, and therefore are far less affected by barrel harmonics than firearms. Projectile propulsion consistency. In air guns, the inbuilt power plants themselves provide the propulsive force to the projectile, so tuning the gun alone is usually sufficient for accurizing as long as the projectile's weights and shapes are uniform. Firearms, however, rely purely on the powder within a cartridge to provide propulsive force, and any slight variations in powder load and rate of combustion will affect the internal ballistics of the gun, even if the projectile weights and shape are the same. This means that in addition to the gun itself, consistent ammunition performance is also extremely critical for accuracy with firearms. While some manufacturers produce match-grade ammunition with smaller tolerances, it is common for shooters of high-precision disciplines to hand-load and fine-tune their own ammunition. Furthermore, the rapid gas expansion that occurs when the projectile leaves the muzzle also barometrically affects flight behavior, so muzzle devices such as flash hider and suppressor can also be used to modulate the escaping gas and improve the consistency of shots. The key to an accurate firearm is consistency. Getting everything to happen the same way for every shot is key to producing small groupings, and there are a large number of issues to be addressed in achieving an accurate firearm. The keys to firing an accurate shot are a firm but not over-tight grip, the ability to get a good sight picture and a controlled squeeze of the trigger. The ability to manage recoil is also important in heavily recoiling calibers, both to aid in possible additional shots, and to prevent the user from developing a fear of the recoil. Determining accuracy. Determining accuracy is not always a straightforward task, as it depends on a large number of variables. Factors affecting accuracy. The accuracy of a shot relies on many different factors, which can be broken down into 3 broad categories: the firearm, the cartridge, and the shooter. Accurizing generally refers to the processes that are applied to the firearm. Techniques relating to producing accurate ammunition are covered in internal and external ballistics, and hand loading, and just like accurizing a firearm, the goal is to produce the most consistent possible results. The shooter must also be consistent, and this means that the fundamentals of marksmanship have to be followed rigorously. Any failure on the part of the shooter to remain focused and consistent can result in a bad shot. It's common to use a bench rest or a vise when evaluating ammunition or a weapon for accuracy in order to eliminate human error. Measurements. Since adjusting the point of impact to match the point of aim is relatively simple with any type of adjustable sights, the primary goal of Accurizing is to increase the precision of the firearm, which is generally measured by looking at the dispersion of a number of shots fired at the same point of aim. An ideal group would be one where all shots land in a hole no larger than the diameter of a single bullet. This would indicate zero dispersion. The most common way of measuring groups then is to measure the edge-to-edge distance of the farthest holes, and subtract the bullet diameter, which gives the center-to-center or CTC measurement of the group. This can be expressed in linear measures, a 1-inch group at 100 yards, or in angular measures, a MOA group. Groups for rifles are traditionally shot at 100 yards, 91 m, where a minute of arc equals 1.047 inches, 26.6 millimeters, and the 1 MOA group is a traditional benchmark of accuracy. Handguns are generally used at closer ranges, and are tested for accuracy at their intended range of use. Also of importance is the number of shots fired. Statistical likelihood says the fewer shots that are fired, the smaller the dispersion will be. 3 or 5 shot groups are acceptable for zeroing the sights and rough accuracy estimates, but most shooters consider 10 shot groups to be the minimum for accuracy comparisons. Defining accuracy. Even defining accuracy can be problematic. An example of this can be shown by the following tests, run by Performance Shooter magazine in December, 1996. The magazine was testing 7 brands of .38 special wad cutter rounds in 3 different revolvers, a Smith & Wesson Model 686 and Model 52, and a Colt Python Target model, with 6, 5 and 8-inch long barrels, respectively. 10 groups of 5 shots were fired and measured from each revolver with each ammunition. Click on the image at right to see a larger view of the graph of average group sizes for each type of ammunition and each revolver. The average group size for the overall test was 72 mm, 2.85 in. Based on average group size, the winner was the Model 686, which shot an average group of 68 mm, 2.69 in, across the brands of ammunition, with a standard deviation between ammunition types of 14 mm, 0.54 in. However, the Model 52, while shooting slightly larger groups at 73 mm, 2.88 in, was far more consistent across the brands, with a standard deviation of only 7.6 mm, 0.30 in, and was the most consistent performer of the test. However, if the ammunition was tuned to the gun, the clear winner was the Python, which averaged just 43 mm, 1.69 in, with its favored brand of ammunition. The Python was also by far the pickiest, however, turning in the largest groups at 154 and 102 mm, 6.08 and 4.0 in, averages with its least favorite brands, for a standard deviation of 41 mm, 1.6 in. Based on this test, answering the question which is the most accurate, becomes a matter of opinion. The answer that would most likely be given would probably be the 686, as it shot the best average groups. However, as the Python showed the best performance with one brand of ammunition, it might be the best choice if that brand of ammunition were acceptable for the application in question. If a consistent supply of ammunition were a problem, then the 52 might be the best choice, since it showed the least sensitivity to differences in ammunition. Testing methodology. As the goal of accurizing a firearm is to improve its accuracy, the way accuracy is measured becomes important. A firearm used primarily as a hunting weapon will need to be accurate on the first shot from a cold, clean barrel, while one used for target shooting may be allowed fouling shots before the first shot for record is fired. Issues of portability or restrictions of certain competitions may limit the alterations that can be made. In addition, every firearm is different, and processes that yield huge results on one may not affect another. Another issue in measuring accuracy is the position in which the shots are fired. The most accurate shooting position is a supported position, such as firing from a bench rest with the firearm well supported by a shooting rest or sandbags. This eliminates much of the shooter's potential for error and will generally result in much smaller groups than firing from an unsupported position. Even for a firearm that is going to be shot offhand, accuracy testing from a machine rest will provide an idea of the ultimate attainable accuracy. Usability. No matter what the potential accuracy of a firearm, it cannot be fired accurately unless the shooter can fire it accurately. A firearm that is comfortable, fits the user well, and provides for a careful, consistent trigger pull and recoil management is not only a physical advantage over a poorly fit firearm, but a psychological one as well. Trigger. The dynamics of the trigger are one of the most important aspects of usability, since any movement of the firearm caused by pulling the trigger can affect the placement of the shot. Trigger pulls are relative, however. Compare a sport like action shooting, which emphasizes speed and uses relatively close targets with large scoring zones on the targets, to bullseye shooting, which uses distant targets with tiny scoring zones. While both types of trigger need a predictable pull, bullseye shooters demand a much higher degree of precision. Analysis of the trigger pull. The trigger pull consists of 3 stages. Take up or pret ravel, which is the movement of the trigger which happens before the sear moves. Break, the movement during which the trigger moves the sear to the point of release. Overtravel, which is the distance a trigger moves after the sear releases. The take-up is the least critical stage of the trigger pull, and individual preferences vary widely. 2-stage triggers, for example, consist of a noticeable take-up, followed by a distinct increase in the force required to pull the trigger, followed by the break. A single-stage trigger, on the other hand, has no discernible movement before the break. Fully adjustable triggers will provide a 2-stage pull, and the option of reducing the first stage travel to 0, essentially making the trigger a single-stage trigger. The break is a far more critical stage of the pull, as it happens just prior to the shot being fired. Here again, individual preferences vary. Some shooters prefer a soft break, where there is a smooth but discernible amount of trigger travel during firing, while others prefer a crisp break, with a heavier weight and little or no discernible movement. The overtravel can be the most critical factor in the trigger pull, as any movement caused at this point will happen as the shot is fired. This is especially important with firearms where there is a sudden release of resistance when the sear breaks, such as in double-action triggers. An overtravel stop will arrest the motion of the trigger just after the break, and prevent movement. Overtravel is not always considered bad by some, as the force of the trigger finger does not impact on the gun directly after sear release. Improving the trigger pull. An adjustable trigger may have ways to adjust all of these stages, plus trigger location. For example, a first stage or take-up adjustment might include weight and travel, a second stage or sear engagement adjustment might include weight and travel, and a trigger stop adjustment would limit the overtravel. While adjustable triggers may provide the greatest level of control, much can be done with standard non-adjustable triggers. Careful hand fitting and polishing of parts, addition of high-precision or adjustable aftermarket parts, or fabrication of new parts can greatly improve most triggers. Care should be taken, however, since trigger work requires a great deal of care and precision, and a bad trigger job can easily render a firearm highly unsafe or unusable. Liability issues. Most manufacturers ship firearms with fairly heavy, non-adjustable triggers, colloquially known as lawyer triggers. This is out of concern for liability. Firearms are inherently dangerous, and allowing the user to adjust the trigger, or even implying such adjustments can be made, exposes the manufacturer to lawsuit. Likewise, manufacturers of aftermarket parts expose themselves to similar liability issues. Sights. A firearm's sights help its user to align the barrel with an intended target. In some cases the only refinement in a target firearm over a standard model is improved sights. Adjustable sights are essential for most target shooting, as they allow compensation for variables such as target range and ammunition type. Firearms with non-adjustable or coarsely adjustable sights cannot give their holders the ability to reliably shoot on target in changing conditions. Improvements in visibility and sharpness of a target image provided by some sights can also improve users' aim and consistency. Typical open sights with a blade, post, or bead near the muzzle and a notch over the breech are good for quick alignment but far from ideal for accuracy. An aperture sight mounted closer to the user's eye and farther from the front sight tightens accuracy by lengthening the sight radius while helping the person take better advantage of the improvement. Some of these peep sights provide precise, repeatable adjustments for long-range shooting with no need for tools. Telescopic and reflex sights offer advantages to people with less experience or poor eyesight by bringing both target and aiming point into focus, while scopes also magnify and brighten the image, though drawbacks such as weight, bulk, and complexity can also affect a shooter's performance. Stocks and grips. A good stock or grip is one that allows the shooter to have a relaxed but firm grip on the firearm. This can range from minor changes such as texturing grip surfaces or adding a wide, beaver tail type grip safety to a 1911, all the way to a custom-built, anatomically designed grip that fits like a glove. Key features are: structure. A firearm that is properly affixed to the stock, allowing the barrel to float freely as opposed to touching other surfaces, will be more accurate. A stock should also allow the action to be affixed securely and provide a good bedding surface, which sometimes requires the use of epoxy resins. Comfort. This allows the shooter to relax and concentrate on shooting. Control. The shooter must be able to hold the firearm on target, and provide consistent movement under recoil. Positioning. The shooter must be positioned correctly and consistently, allowing easy use of the sights, and a clean trigger pull. Gripping surfaces. Gripping surfaces, particularly on handguns, are often designed to provide a large degree of friction to prevent the shooter's grip from shifting. This can be done by either using a material that provides a high friction, such as rubber, or by adding texture to the grips. Traditionally, wood grips and stocks are provided with checkering, a process where V-shaped grooves are cut into the wood at an angle to each other, leaving a pattern of pyramidal projections in the wood. Another process uses a punch to leave a random pattern of dents in the surface, called stippling. This process is better suited to complex curves than checkering, and is often found on anatomical grips. Handguns with plastic frames will often have stippling or checkering molded into the frame. Handgun grips. Grips for handguns, especially ones used in single-handed disciplines such as bullseye and Olympic handgun shooting, are critical to good accuracy. The grip provides very little control compared to a rifle stock, and so a good fit is required to give the shooter control over the gun and isolate the trigger finger movement. Fortunately, aftermarket parts makers provide a wide range of grips for handguns, allowing shooters to find grips that are suitable for their hands. Competition handgun grips are anatomically shaped, and are often custom fitted to the shooter's hand. An ideal grip will fit the contours of the shooter's grip, so that the knuckles fall into position the same way every time. The ideal grip should allow the shooter to repeatedly grasp the gun, bring it up to shooting position with eyes closed, and be correctly aligned and on target when their eyes are opened. This means the grip provides a consistent placement, and minimal corrections when aiming. Contrary to commonly stated rules of thumb, the handgun should not line up with the forearm when gripped, but rather point slightly outwards, so that when held to shoot, the sights line up with the shooter's eye. In cross-dominant shooters, the angle will be more pronounced. Thumb breasts, finger grooves, if well fitted, and palm rests all provide control over recoil. An adjustable palm rest is a desirable feature as well, as it allows the grip to be adjusted to fit the shooter's hand as it swells and contracts over time. Rifle and shotgun stocks. Stocks for long guns are not as often changed as handgun grips, but a well-fitted stock can make a significant difference in accuracy. In shotguns in particular, the placement of the shooter's face on the stock provides the rear aiming point, and the correct drop and cast off can greatly enhance accuracy. This was traditionally accomplished by steaming and bending the stock, but a simpler solution for modern guns is a set of shims that alter the angle of the stock. Rifle stocks have similar issues of fit, and though the use of sights makes this less vital than in a shotgun, a good fit still helps the shooter to relax and concentrate on fundamentals. The shape of a rifle stock should be suited to its intended use. High combs and vertical pistol grips are ideal for high-mounted target sights or scopes, and careful, deliberate shooting such as encountered in traditional target shooting, metallic silhouette, or varmint hunting, as they provide a maximum point-blank range and ideal trigger control. However, these features are not well suited for a typical hunting or action shooting rifle, where the rifle must be brought from a ready position to a shooting position quickly and smoothly. This use favors low sights or scopes, and a shallow pistol grip angle. Rounded forearms are well suited for firing from offhand, while a square-bottomed forearm provides a stable base for shooting off of a sandbag or other rest. Recoil is also a key issue in rifle stock design. Heavy recoiling rifles should have wide butts, with a good recoil pad to absorb the force of recoil, and a comb that is straight or slopes down towards the action, so that it does not push into the shooter's face under recoil. Other features of target or varmint stocks, such as thumbola grips, can actually injure the shooter if used in a heavy recoiling hunting rifle. Some target shooting disciplines allow the use of various devices to help support the rifle, and these are often mounted to an accessory rail beneath the forend. Target slings, unlike carrying slings, are used just on the offhand, usually with a hand stop, and provide stability to the shooter's hold. Palm rests are another device that can be attached to the rail, to allow a shooter to lower their offhand and place their elbow into their body for support. Target stocks also are available with a large degree of adjustment, including length of pull, drop, comb height and angle, and butt plate angle and curvature. Time considerations. The bullet does not leave the barrel as soon as the sear releases, rather, there is a delay between the release of the sear and the bullet exiting the barrel. During this time, any movement will move the firearm off target, and so this time should be minimized, especially for firearms that will be fired from an unsupported standing position. This delay can be broken down into two sections, the lock time and the bullet dwell time. Lock time. Lock time is the time between the release of the sear and the ignition of the cartridge. A lengthy lock time gives time for the shooter to drift off target, and so it is advantageous to minimize the lock time and reduce the window for error. Reductions in lock time are generally performed by lightening parts that move as part of the firing operation, such as the hammer and firing pin or striker, shortening to distance parts that move as part of the firing operation have to cover, and using a more powerful spring. Further reductions in lock time, to near zero levels, can be achieved with electrical primers. Bullet dwell time. The bullet dwell time is the time between cartridge ignition, and the time the bullet leaves the barrel. Like lock time, dwell time is a window for error, and can be minimized with a faster bullet or a shorter barrel. In some cases, a shorter barrel is desired to reduce dwell time, but without losing the sight radius of a longer barrel. In this case, a sight extension tube, or bloop tube, can be used. This is a tube that fits on the muzzle end of the barrel, providing support for the front sight, but that is bored to much larger than bore diameter. This provides the sight plane of a long barrel with less weight and dwell time. To put lock time and bullet dwell time in perspective, the lock time of most conventional bolt-action rifles varies between 2.6 and 9.0 milliseconds, while after cartridge ignition most rifle bullets travel through a high-powered rifle barrel bore in 1.0 to 1.5 milliseconds. Mechanical bolt-action rifle trigger systems with a sub 2.0 milliseconds lock time are applied in most purpose-designed high-end competition rifles. Clearances and tolerances. The terms clearance and tolerance are very often confused and misused. Clearance is the distance between the surfaces of mating parts. Tolerance is the allowable variation of a dimension from its nominal, desired, value. For example, a bolt with an outside diameter, OD, of 0.697 inches which is operating in a receiver with a bolt raceway inside diameter, ID, of 0.702 has a clearance of 0.005 inches. If the bolt OD has a nominal OD of 0.698 and a tolerance of +/0.001, then the bolt OD can randomly vary from 0.697 to 0.699 along its length, which will allow the bolt clearance in the 0.702 diameter raceway to vary from 0.005 to 0.003. Further, if the raceway also has a tolerance of +/0.001 from the nominal of 0.702, then its ID can vary from 0.701 to 0.703 along its length. That combination of tolerances can allow the bolt clearance to vary from 0.002 to 0.006. The point at which the 0.002 clearance occurred would likely cause binding and malfunction in most operational environments. To ensure consistent, repeatable lockup, clearances between moving parts must be kept to the smallest value that will allow proper operation of the mechanism. This goal can be achieved by carefully hand-selecting parts and precisely fitting them together, or by manufacturing new parts, bolt, receiver, barrel, etc. to precise dimensions using much tighter tolerances than production components. The best fits are generally attained by selecting slightly oversized parts, or altering stock parts to form an interference fit, and then lapping the mating surfaces to attain the desired fit, clearance. Clearances cannot be too tight, however, or functionality will be compromised. This is very important in automatic and semi-automatic firearms, where there is a certain amount of energy extracted from the firing of the cartridge that must be used to cycle the action. Overly tight clearances mean that there is no place for lubricant and dirt to be, and this can bind the parts. However, except for cost considerations, it is always beneficial to minimize the tolerances applied to the manufacture of mating parts. In some cases, stock parts are not sufficient for the task of producing a finished product with sufficiently tight clearances. In this case, it may be necessary to use specially fabricated parts, built either with minimal clearances, but to a very tight tolerance, or parts that are oversized and intended for hand fitting. Barrel. The barrel is one of the most important factors for accuracy, as a poorly made barrel may be beyond correction. Even a quality barrel must be well matched to the cartridge it will be firing. In most cases, it is not practical to fix a barrel whose bore is worn out, poorly or unsuitably rifled, or the wrong bore diameter. The primary exception to that is rimfire barrels, which can be inexpensively bored out and relined with a commercial barrel liner. If the barrel is unsuitable and relining is not an option, then an aftermarket or custom barrel is the best solution. However, if the bore is good, then there are a number of operations that can be done to the barrel to improve upon its accuracy. Bore. Ideally, the bore must be cylindrical and the rifling geometry the same down the length of the bore. Some airgun rifles have a short cone towards the muzzle to improve the speed of the bullet. A slight gain in the rifling twist, or a slight tapering down of the bore, will still ensure the tight fit of bullet to bore, so when selecting a barrel, the tighter or faster twist end should be chosen for the muzzle. The twist of the rifling must match the intended ammunition for best accuracy. Rifling with too slow a twist will not stabilize long bullets, causing them to precess in flight. At its worst, this can result in the bullets tumbling in flight and keyholing, where bullets strike the target sideways. Too fast a twist can also be a problem, as it can magnify problems in the bullet. A bullet whose center of mass is slightly off-center will diverge at a rate proportional to the rifling twist, so excess twist will result in greater dispersion. In practical terms, this is only a problem for rifles chambered for common military calibers where a variety of different loads exist. For example, the M16A1 rifle is unable to accurately fire bullets that are heavier than 3.6 grams, 55 gr, due to barrel twist that is too slow to stabilize heavier bullets. Precision rifles typically come with barrels that are either tailor-made for a specific ammunition load or made according to the buyer's specifications. Barrels can also benefit from lapping, not only because it makes the bore a more consistent diameter, but also because it polishes the bore. Barrel lapping should be done with the tool moving in the same direction as the bullet will move, so that any imperfections in the barrel will be smoothed out and thus not interfere with the passage of the bullet. A smooth, polished bore will not only hold the bullet better, but also reduce barrel fouling. Chamber. Of great importance to accuracy is the fit of the ammunition to the barrel. The chamber should be concentric, and the throat size just slightly larger than the bullet diameter. The cartridge must headspace correctly, be held firmly in place, concentric to the bore, and the bullet must fit the bore and be guided to engage the rifling cleanly. Once the bullet is engaged in the rifling, with a good seal and coaxial fit, it must stay that way. It is often possible to shorten a barrel slightly by removing material from the breech end and recut the chamber, which can correct many problems in the original chamber. Crown. The crown is the muzzle face of the barrel. The crown's integrity is critical for two reasons. It is the last part of the firearm touched by the bullet before it exits. As the bullet clears the crown, it will release upwards of 34 to 69 megapascals, 5,000 to 10,000 psi, of back pressure, which must be as uniform as possible. While many barrel manufacturers recess the crown to protect it from accidental damage, it can still be damaged over time by cleaning rods that are too hard. It is also not uncommon for factory crowns to be cut slightly off-center, so that one side of the bullet exits slightly earlier than the other, and this will result in the bullet being pushed away from that side, causing a significant deflection in its path. A crown may be recut with relative ease, and this can fix any problems caused by a defective or damaged crown, by ensuring an even release of the bullet. Stress. Any machining process on a barrel, whether it's boring, rifling, or turning the outside contour, will produce some stress in the steel of the barrel. This stress can cause the barrel to expand unevenly as it heats, causing shots to walk as the barrel heats and cools. To prevent this, careful post-machining heat treatment is often used to stress relieve the barrels. The ammo.
Please subscribe and thanks for watching.